is, well, Stark-Wannier Hamiltonians that I'm going to define in a minute. And, well, I introduce you to the questions, tell you something about the known results, and then show you the results that we got with Sasha on this question. So what is this about? I guess that actually most of you know about Stark-Wannier Hamiltonians, but for those who don't, here is what it is. So we are working with actually very simple objects. We consider a simple differential equation. So we consider an operator on the real line, on the whole line. And we're essentially interested in spectral problems. So for example, consider the eigenvalue equation, which is a second order differential equation. The potential V of x that appears inside this operator is going to be periodic, one periodic, just to fix ideas, and it's going to be assumed to be real analytics, though part of what I'm saying does not really depend upon that, but we're going to use it later on. And epsilon is just a positive constant. As its name suggests, it's going to be small. Well, actually not. It's going to be small just in the introduction in presenting known results, but now in the talk, epsilon will be rather of size 1. Even though the epsilon small case is of interest, it has a particular interest, but okay, we'll see that. So what is this operator? So this Stark-Wannier Hamiltonian, as it's called, is, well, when it was first introduced, it was introduced as a model for a Bloch electron, which means an electron inside a periodic field, which is V of x. Of course, it's a very simple electron. It's confined on a one-dimensional space. This is where the Wannier part comes from, because it's well known. Wannier has contributions to the spectral theory of, well, actually, physics, right, of periodic operators. And so this Bloch electron is moving additionally inside a constant electric field, which is modeled by this term minus epsilon x. Right. And so people were interested in what happens if you take the electron inside a periodic medium and submit it to some external electric field. Now the thing is, people, actually this was in the 30s, I think, was maybe even before the 30s, late 20s. But people realized quite quickly that one of the main problems they had, of course they could come up with some theory, with some tries to solve the problem analytically, but the main problem that they had were experimental, in the sense that if you try to do experiments for electrons, the other effects, for example, the fact that an electron essentially never moves alone, right, inside some solid state medium, that you have many things inside your medium which is called phonons, which are like vibrations of the lattice, and all these effects were actually much too big so as to find out what were the theoretical predictions of the spectral theory of this object. So the first system that this object was supposed to model was actually not suitable at all to make experiments. But it happened that in the 70s, actually no, it's more than 70s, actually it's more in the 80s, 90s, people started to build material where, again, the movement of a single electron was actually well modeled by such an operator, but this time these materials actually could really be built in such a way as to encompass a one electron approximation, and that other physical effects, except for this Hamiltonian, could be neglected, right? So this is what they call electrons in semiconductor superlattices. So essentially the main problem is the following, is that if you look at here, if you take a true Bloch electron in a constant electric field, the main problem is that the wavelength of your electron is about the same size as the atomic distance, right? And this gives rise to too many parasitic terms. Here, you are working with artificially built lattices with semiconductors, which have spacings between the, let's say, or the period of the lattice is much larger than actually the wavelength of the electrons or the particles traveling in there.
Are these materials one-dimensional?
These materials are one-dimensional in the sense that really they confine them on a tube, right? And actually, more recently, even in the 2000s, actually, people started playing with cold atoms in optical lattices. So what they do is they create some Bose-Einstein condensates, and they can create a single one, so they really have a single electron. And then what they do is they shine some laser light at a given frequency, which models your periodic field. And using magnetic fields, they can constrain the Bose-Einstein condensate to be essentially one-dimensional. And for example, So, and for such things, there were actually experiments where people saw what will be the main subject of our talk, meaning the Stark-Wannier ladders, right? So they saw them experimentally. They saw actually the resonances in the fact that you have energies where the transmission, right, is going to be much larger than at other energies. Okay, transmission. So you try to have one of these cold atoms, because you really can single them out, and you try to transmit them through some medium, which is essentially a laser light. Okay, and you really see that at some energies it works well, and at others, well, tough luck, things get reflected back, and you have a much smaller transmission. Okay. Well, actually, in these cold atoms were very useful also for, if you think of Anderson localization or quasi-periodic media, because people were able to build quasi-periodic potentials by just shining two lasers to each other, right, at incommensurate frequencies. So then, actually, the resulting wave is going to mimic a quasi-periodic potential, and people were able to see, actually, cold atoms localized inside this quasi-periodic medium. So these are famous experiments from the end of the year, in 2008, I think, they published a paper in Nature 2008 on this. And so we have a number of experiments coming up. So, but let me come back to my model. So this was just to motivate why one would consider such a simple equation, right? And one would be interested in the spectral theory or the resonances of this. So spectral theory, well, one simple thing, right, is that first the spectrum of this operator for any value of epsilon, right, non-zero, it's also true for epsilon equals 0 except for the first statement, but for any value of non-zero epsilon, the spectrum is actually the whole real line, and it's purely absolutely continuous, right? And thus one can try to actually define resonances by defining the analytic continuation of the resolvent, right? So this seen as a function of z. You can try to continue it from the upper half plane to the lower half plane through the spectrum, okay? And the resonances are just the pores of this resolvent, okay, if they're right. And so the Stark-Wannier ladders, the name ladder comes from the following fact. In this case, the resonances, all of them, right, are going to form actually many epsilon periodic lattices that are parallel to the real line, just because of the following property. Remember, V is one periodic, so it's invariant by translation by one, and the conjugation by translation by one. This one, of course, the Laplacian is also, oops, what happened here? Yeah, I think I'm going to do the following. So this is heavy enough to hold the cable. And so, as I said, V is one periodic, so invariant by conjugation by translation by one or by any integer. The Laplacian, of course, is also invariant, but if you conjugate epsilon x by one, by translation by one, what you get is that you get just a shift of epsilon, or minus epsilon, sorry, if I do it this way. And which means that for the resolvent, I get the following equation, right? And so the resonances, the pores of this one and the pores of that one coincide, which means that the resonance have to be on epsilon periodic, right? Set of resonance has to be invariant by translation by epsilon. Okay. And so the main question is, what do these resonances look like? Okay. So there are many works, both in math and in physics. Actually, it's interesting when I search for the literature. What you saw is that there was, of course, first a lot of work in physics. Then the problem was taken up a little in the beginning of the 80s, and there was, during the 80s and the 90s, there was a lot of work, and essentially work died out in the year 2000, 2002, right? This is roughly where the last work in mathematics, that I saw ended, and there was nothing really new over the last 15 years, right, almost. And, well, we may see why this is the case, okay? So the proof, what people were able to prove from a mathematical point of view is that in various regimes of nu, what do I mean with regimes of nu is, can be V large, right? It can also have to do with the regularity of V, right, which is an important parameter. And epsilon, of course, you can take epsilon times 1, epsilon small is one of the favored regimes that were studied. Well, one had there are proof of existence of resonances, right? So people prove that you actually have some resonances. Of course, once you have one, you have a whole ladder, right? But they didn't get a complete picture of what these resonances are. And this was also done actually not only in one dimension, but also in higher dimensions, right? There are proofs also in higher dimensions. And one of the questions was how to determine the ladders, right? But of course, I mean, determining the ladders is certainly going to be more complicated. It's going to be more complicated than determining the eigenvalues of a 5 by 5 matrix, right? Which is already, well, 6 by 6, okay, to make it even more complicated, a 6 by 6 matrix, but you know that you don't have the real analytic way to do that, right? So you use asymptotic parameters, and the asymptotic parameter in this case is going to be epsilon small. So people try to determine what are the ladders when epsilon is small. So, and the analysis, well, so this is a semi-classical limit, so it was done first by physicists. One group around Vladimir Vuslaev also developed this analysis, even though he was in the physics department, right? I'm not sure we can really call him a physicist. But they developed a nice semi-classical analysis, but the semi-classical analysis had one drawback. It could only be done for very special potentials V, namely potentials that have finitely many gaps, right? So let me just remind you here. It's well known that if you look at, well, not only in one dimension, higher dimension, but just one dimension, well, the spectrum of your free operator, right, is a union of bands. And in one dimension, usually, so the connected components of the spectrum, which is only pure absolutely continuous. Yeah, I'm gonna, at some time, I'm gonna trip on this, and, but okay. Well, I jump on it before Thanksgiving.
Jump on it.
But I'm not sure, actually, I'm gonna break the plastic, that's the only thing I'm gonna gain. But I think,
Want me to do it? You continue your
Can
talk.
you-
I'll
can
do
you-
it.
I think you have to introduce it this week.
No.
No, trying to turn the terrain.
The cable is in the way.
Okay, so,
Maybe to turn the terrain.
here's the, wow. Well, you're gonna achieve the same result as me jumping on it, actually.
Turn it around. You sure?
Well, I think we're gonna stop here, actually. Now, you know that this is broadcast live all over the world, right? So, gentlemen?
You see how it is there.
Yeah, oh, that's correct.
Just leave it.
Yeah, okay, let's, well, that's fine. I'll leave it where it is, it's gonna be, I'll be careful. Okay, so, so you have, in general, you have infinitely many of these gaps. So why, let me now explain what this analysis was about, and we'll see in the course of this explanation why the number, or the finite number of gaps is important. So, what's the idea? The idea is that actually, these bands, or actually what I call the band functions or the dispersion relations in physics for these bands, well, they can be used to build up an effective Hamiltonian to analyze minus d 2dx2 plus v plus epsilon x when epsilon is small. So what are the band functions? When the band functions are just the following thing, you can try to solve the eigenvalue equation for this, right, with quasi-periodic boundary conditions. Right? If you impose quasi-periodic boundary conditions, what you are going to find is that the spectrum of the operator is going to be discrete, and the frequency, the quasi-periodic frequency, which is called the quasi-momentum k, you fix this one, you get a discrete spectrum, and the eigenvalues are just the functions ej of k, right? And these functions are naturally, because of v being one periodic, 2 pi periodic, right? And these functions I just plotted here. Actually, here, a star is equal to 2 pi. Right? A star here is equal to 2 pi. And so the spectrum of the operator minus Laplacian plus v is just going to be the projection of these curves onto the axis x equals 0. Okay. Now, to construct the effective Hamiltonian, what you do is you just replace your minus Laplacian plus v by any of these bank functions, and epsilon x is going to be your semi-classical parameter, right? So it's going to be replaced by the momentum. This plays the role of momentum. And you look at the characteristic variety, your symbol is just ejk minus xi equals e. Okay, so let's look at how this looks like. So here's a picture of the characteristic variety, right? In the case when you have only two bands for nu. Nu has two bands, right? V has two bands. Actually, you don't see it because the picture could go on over there, but we assume that this branch goes up to infinity. What's this picture now? The three dimensions, xi is going to be only real in this picture, but k is going to become complex as well, right? The branches that you see here for xi real and k real, right? This one and this one and this one are actually the branches when the energy E is inside the spectrum, meaning that you have real solution k and xi to this equation, right? So these are characteristic, these are parts or connected components of the characteristic variety inside the real. These branches, right, these tori, are actually connected components of your characteristic variety inside the complex, right? So these real parts, as usual, give rise to quantization conditions, right? These real parts give rise to quantization conditions. And the quantization conditions, you get one per band of spectrum of your periodic operator. Here you have one for this one, and these are infinite, so they don't give rise to quantization conditions. They give you something at infinity, right? It gives you the decay of your thing at infinity. And this is completely complex, right? Because, why is the picture in this direction? It's because my potential is minus epsilon x, so the forbidden region is near minus infinity, and the allowed region is near plus infinity, right? So any particle is going to flow out in this way, and here it's going to be blocked and decay. Okay, and so what you do is to each of these things you attach a quantized value, right? And of course, because of the ladders, this quantized value is going to be shifted by any integer multiple of epsilon to give you the ladder. And this will give you the real part of the resonances. Okay? Then how about the complex parts? Well, the complex parts come from the fact that if you take some mode that is living here, if you want it actually to decay at infinity, it cannot go in this direction. Here you have big forbidden infinite sized wall. So it has to go to the other side, to the C. Right? So it has to go to this side of the potential if it wants to go off to infinity. Okay? And so what you do is you have to tunnel through these tori. And to tunnel such a tori, there is a probability, a tunneling probability, which is computed with an action. Right? And the action is just given by this. Okay? So actually these integrals are purely imaginary. They have the right sign for the thing to be negative and large. And you see that when epsilon is small, these actions here are very small, meaning that the imaginary part of my resonances, a priori, is going to be exponentially small in 1 over epsilon. Okay? So that's the picture. But of course, this only works if you take a double, right, for example, right, just take a potential of two values. This only works if there is no resonant phenomenon between the quantization conditions, for example, for this connected component of your characteristic variety, and for this one, right? If they do not resonate, then you are fine, and essentially the states here are going to tunnel through and they won't feel this. But if the eigenvalue created by this one and this one are too close to one another, right?
Frédéric, excuse me. You say that this is small, but if epsilon is small, this is big?
No, what is small is the imaginary part. Once you take the logarithm, it's big. That's correct. Here we have log of imaginary part.
Ah.
This
So
is
it's big,
big, very negative, right? And the imaginary part is small, exponentially small, right? There is a log here. Okay. And so
there's also some k's and n's confused, right?
the n, no, it's because I assume that I have n gaps. So you see, you have to go through n tunneling processes.
Yeah, but you have jk there and zjk.
Sorry?
Zjk.
Yeah, ZJK. Why? It's because I take the K is going to be the index, right? Because they all have the same, they're all the same.
Yeah, but then you integrate over K on the right.
Oh yeah, sure, it's not the same K, I agree with you. This K is a mute variable, right? It's a local
So
variable.
K index is the ladder index.
Exactly, the K index is the ladder index.
Yeah.
Okay, and the J index is the band index. Every band gives, or every spectral band gives rise to a ladder, right? Except the last one, which is the way to infinity.
Yeah.
Okay, and the K here is just a mute variable, right? Okay, should change this. Here too, it doesn't have anything to do with this one, even though it's written the same way. So, but of course, as I said, this is not going to work if you have resonant phenomena, so another type of resonances, between the different bands, right? And, well, what happens is that, so this resonance phenomenon can occur, and what happens that is, well, you have to imagine these imaginary parts are exponentially small, right? So, if you think of the ladders, you have something, so this is, well, of course this is not too, I'm going to, drawing exponentially small things on the board is always difficult. So here you have your lattice, right? Spacing epsilon. Here you have something which is e to the minus c epsilon. And the next lattice, coming from the next band, is going to be, so this is, for example, for this band, so the closest one to the real, and the next one is going to be somewhere here. The spacing is the same. And the distance is going to be e minus c. So for example, C1 over epsilon. So you see that these can be exponentially small, right? Exponentially close together if here you have a resonance condition. But of course now, if you have infinitely many bands, all of this is going to pile up. You're going to have lots of these ladders piling up very close to that one. Okay? And all these resonances could fill the gap. Here you're more or less at the safe distance. If you have only 2 or 3, you're at the safe distance because you can come up with more or less simple conditions that avoid the second, the third, and up to the nth to be resonant with the previous one. But if you have infinitely many, right, well, it's not going to be that easy, and actually, so you can have a quite complicated, and there's a paper of Avron, and the paper of Avron in '82, where actually, doing numerical calculations, right, he found out, or it looked to him like the fact that the properties of actually the imaginary part of the resonances is going to depend on the number theoretical properties of epsilon, right? So not only on its size, but it's really going to depend on, for example, the continued fraction expansion of epsilon. Let me just show you 2 graphs I took from, actually, this one is taken from the paper of '82 by Avron, and this one is taken from a review by physicists in 2002. So what do they show you here? What is gamma? Gamma is the resonance, actually the imaginary part of the resonance, right? Gamma is the imaginary part of the resonance. F here is my epsilon. It's the strength of the electric field. And what they plot is 1 over f, so f goes to 0, 1 over f goes to infinity, right? And here it's a plot of what is the size of this log imaginary part of z for the first band of resonances, the closest one to the real axis, right? And how it changes when you let f go to 0. Right? And you see you have these things going on, these zigzags, right? Which are more or less rather random looking. And here they do the same thing, except that they did not scale using the logarithm, right? They just drew it in another scale. They took a logarithmic scale here in the picture. So the picture looks somewhat different, but it's essentially the same computation. Okay, and you see these spikes, and there is some kind of random occurrence of these spikes. Okay, and so what are we going to do? Well, we are going to try to say something interesting about these resonances, of course. And therefore, let me first define properly what the resonances are. So I take now V to be an entire potential. And I look now at my equation as an equation over the whole complex plane. Right? I consider an equation in the complex variable. I call it complex variable x. And what I can show, or actually this was shown by Boslav, is that you can find 2 solutions. One with a prescribed behavior for any energy, with a prescribed behavior at minus infinity, and the other one was a prescribed behavior at plus infinity, right? Two Yost solutions, as they are usually called. And well, this is just, right, what you do essentially, you take the Yost solution for the free Laplacian, forget about, right, the potential V. When you're at infinity, when x is very large, V is periodic, entire, right? So it's going to be, well, if you don't go too far in x, right, but x here means that real part of x goes to infinity, imaginary part of x stays in some finite domain, right? These things, of course, are not uniform when x goes to infinity in modulo, right? This means really that x goes to minus infinity, means that real part of x goes to minus infinity, and the imaginary part of x stays inside some compact set, right? And in this case, of course, this one is going to be dominant, okay? Because just V is entire, so in any kind of, it's periodic, so in a strip it's going to be nice and bounded.
So if I ignore periodicity and set epsilon equal 1, it would have been area.
Yeah, exactly, sure.
This resembles right exponential.
Of course, that's exactly the right thing, because exactly. That's, well, if you do what you said, you see that you get area here, right? Or you get the first term asymptotic of area, right? Because it's going to be x to the cube, to 3 halves, sorry. Right? You're going to get x to the 3 halves, just like area. That's correct. And now, because the equation V is supposed to be entire, but also real symmetric, right? So it's real on the real line. And then, well, what you see is that obviously if psi x e, so these solutions are actually entire functions also of energy, right? You can show that these solutions are entire functions both of the x variable and the energy variable, comes from this coefficients of the equation. You can look at the solution psi star plus, which is just psi plus, there is a plus missing here, at x bar e bar, so the complex conjugates of x and e, and you take complex conjugation of this solution. This again, because of the real symmetry of the equation, is again solution to the equation, right? And you can now write psi minus as a linear combination of psi plus and psi plus star, right? That is W star comes from the symmetry and the properties of this near minus infinity, right? Because this thing essentially at minus infinity is going to look like a real, okay? And what you see is that, of course, well, this is second order differential equations. W of E does not depend on x. The function here is an entire function, right? And it's going to be epsilon periodic. And the reflection coefficient is nothing but the quotient W star by W. Okay. This reflection coefficient is epsilon periodic and it's going to be meromorphic over the whole complex plane, but in the upper half plane it is analytic, right? And on the real line, it has modulus equal to 1. And the poles of this function R, of the reflection coefficients, are the resonances, right, of my operator. These are the things we want to study. So the important thing is that the reflection coefficient is epsilon periodic. So what we're going to do is we're going to look at, as we are interested in negative imaginary parts, we look at the inverse of the reflection coefficient. This thing is going to be analytic in the lower half plane, and we're going to expand it in Fourier series. And what we want to do is compute the Fourier coefficients. Right? We want to compute, as well as we can, the Fourier coefficients of the inverse of the reflection coefficient. What we're interested in is computing the poles of the reflection coefficients, meaning the zeros of this function. Right? We want to compute the zeros of this Fourier series. So to compute the zeros of this thing, we compute, or try to compute, the Fourier coefficients, right, of this series. And we are interested in one thing. We are going to look for the resonances. And this is different from what from the problem that was studied when in the works I actually quoted in the introduction. We are not interested, we won't be interested in the resonances close to the real axis. We are going to be interested in resonances that are very deep inside the complex plane. So they must, if you think the heuristics, I mean, if you take the reasoning that was done for epsilon small, or the analysis that was done for epsilon small, if you take this as heuristics, these resonances should depend really on the fact that your potential has infinitely many bands, right? Otherwise, you would expect that if it has finitely many bands, there are finitely number of ladders, and below that nothing happens. You don't see anything. But we'll be interested in what's happening below that, right? For the cosine, it is well known that minus Laplacian plus v has infinitely many bands, right? Yes?
Is it, what is n in the exponential?
Well, it's m. N is m, thanks. I need to correct that. Well, take v to be the cosine now, and then what we obtain that if you look at what's happening, so for m large, the m's Fourier coefficient, well, is asymptotic. Rather say it's logarithm, but it's asymptotic to some constant times square root of m times this exponential, right? And well, here is the second part of the title pointing its nose. Minus 2 pi I omega m cube, right? So this is an oscillatory term which oscillates with a frequency omega, but in the coefficient numbers, it's like m to the cube, plus some term which is actually a modifying term, because this, when m gets large, decreases, right? So you have a smooth cutoff, plus some error term, which is smaller than this, right? You have some error term, so you have, but it goes to 0. Okay, the error term goes to 0. And this estimate is locally uniform in epsilon positive, which means that you cannot take epsilon going to 0, right, in this estimate. It's not going to give you the right result. It's not uniform in all m and epsilon. It's just locally uniform for epsilon positive.
Yeah, but there is another question.
Yes?
It depends also on the sign of m. How the summation is over.
There's no summation. That's just...
No, I understand.
Oh, yeah, sure. This thing is why I'm here is m going to plus infinity, right? Here, just take m going to plus infinity. The plus is missing. Why? Because I'm interested in imaginary part of E very negative. So this will give you a natural cutoff just due to the fact that you have a Fourier series, right? It's the other part of the Fourier series. The negative coefficients are going to die out just because of this. Okay? Right? And then the Fourier series, you have a periodic function, and you're interested in what happens in the lower half plane. So the only important Fourier coefficients are the ones with positive number, right? Because the remaining ones will be taken care of by the fact that you're in the lower half plane.
Just a second.
Sure.
I'm confused. So there's
M here is n.
epsilon goes to 0, so the one
Epsilon is
side
positive.
goes to
Epsilon
zero.
doesn't go to 0, but this says that epsilon does not go to 0.
Okay, epsilon is positive.
Yes.
So you say, I'm just going to throw away all the negative m's
Yes.
because they will be unimportant when epsilon is actually small. That's what you're still saying.
No, I'm saying that they're going to be important when the imaginary of part of E is large negative.
E you make large
Exactly.
negative.
E will be large negative. Right? What we wanted to understand is what happens if you have infinitely many bands. Is there something we can say?
Okay, so
E will be large negative imaginary part.
So you'll have an exponential sum that's increasing exponentially.
No, what we have, well, you see what we have in a minute, okay? I'm going to write it down. But what is important is that this E large negative kills all the negative terms, right? Because you have minus I times I, right? Times a negative, which is going to be nicely decaying. Right? If I look at the imaginary part of what's inside the exponential.
This funny term in the middle of the exponential minus 2m log
Exactly, this regularizes thing.
2 pi m over e, right?
Yes?
E again, right?
Yeah, it's E, well, yeah, it's just a constant that comes out. Could be something, but here it's E, right? It comes out of computations.
There's no I.
There is no I, no, this is real. This gives you the decay, right? This thing actually at infinity is decaying. But,
Do we have also, I'm sorry.
sure, of course.
We have something like Parseval in order to control Pm that they are not big
Because there's an e in the
Yes.
because otherwise your argument doesn't make
No, sure. Of course, you have Parseval. You have Parseval. Sure, you're right. You're right, because this is this, actually.
Yeah, I understand. You have Parseval.
Right? This is this.
right.
So only what matters is positive.
Exactly. The only thing that matters is actually large M, not only positive, right? Really large M's. These are, if you look at imaginary part of E very negative, these are really the only ones that count.
Right, just trying to do some basic algebra. E to the pi minus log with all these things. You can simplify it somehow, right? It will be this expression under log raised to the power minus 2m in front of the
Yeah, sure, you're right, you're right. That's correct, actually. That maybe you're simpler to write, because, no, that may be simpler to write. What I don't remember is,
decay of all the
the only important thing is that this is m log n, right? It's the principal part, right? Otherwise, the remaining thing you can put out again as some power of m. Okay, you can take it out. So actually, the true power of m is going to be
m to the power minus m, right?
exactly. It looks like m to the power minus m. Yeah,
Minus
sure, that's correct. You can take it out in this way. Yeah, sure. Sure. That's fine. So, and so, as we said, when the imaginary part of e goes to minus infinity, actually what you are really, more or less, this function behaves like this sum. Of course, it's not completely true. You have delta of m here, right? And changing things a little bit can have effects, right? But nevertheless, what you get is some modified exponential sum, cubic exponential sum, right?
So he keeps it up there to just make clear that you have s is equal to
Exactly.
an imaginary negative number, so that m log m has to dominate.
Exactly. No, but you could also remove the constants that are in there. You still have the m log m.
Yeah, sure.
But
but
this
that's
is what
the
he's
point
saying.
Why
He's-
you write it like that.
Yeah, exactly. Of course. The point where I write m log m instead of m to the power minus m is this. But what he was saying, I think, is you can take out the constant and change this factor and get rid of the constant, right? Which is also correct. But it won't change much what you're doing later on anyway. Okay, and so, well, we need to, so one of the things would be first to understand what happens to such functions, right? And can you say something about the zeros of this? Okay, well, unfortunately, we were not able to do much, right? So what we're going to do is we're going to make an assumption on what happens with omega. This is a parameter we can control because it's just depending on the field, on the electric field, right? And we'll be interested in what happens when omega is actually irrational. When omega is irrational, we don't know how to control this yet.
Rational or irrational?
When it's irrational, we don't know how to control it. And I'm going to show you what happens when it's rational. Okay? So take a rational frequency. And then assume that it's P over Q with P and Q co-prime, P less than Q, right? And then what you can show is the following. If you set Xc to be some neighborhood of Xc into the neighborhood of Xc modulo Q, right? That's the precise definition. Then when you let the imaginary part of E go to minus infinity, you have that the inverse, the main part of the inverse of the reflection coefficient behaves in the following way. So you need a few notations. You get a new sum, but just over the integers belonging to this set of what? So what is this? Rho is going to be very large because it's exponential minus pi imaginary part over epsilon. So rho is a very large parameter. Okay? So you get e to the rho times some coefficient, which is oscillating, plus I pi, well, you can read it actually, plus some error, which is small, plus some function, which is actually, so that's a remainder term, which is not small, right? Rho is something very large, so this is also exponentially large, but it's much smaller nevertheless than this. Right here you see, because of my condition here, or actually, just because of the expression, this is going to be of size e to the rho. Right? This thing here is going to be of size e to the rho. The real part of this thing, because of this condition, is not going to vanish. Okay, and so this is size e to the rho. So this function that you have here, it's large, but it's nevertheless smaller, much smaller than that one. Okay, and so if you want to understand what the zeros of this thing are, which is what we want to do, you first need to analyze this. And what are these coefficients? Well, these coefficients are actually complete cubic exponential sums expressed in the following way. So just this function, e to the minus 2 pi I pl cubed minus ml divided by q, fix p and m and q. Right? Look at this as a function of L being an integer variable. Of course, it's a Q periodic function of L, right? Because of the e to the 2 pi I in front of here. right? So this function is Q periodic. So what you're doing, you're just summing these exponentials over one period, okay? And you get these as a coefficient in front of this, okay? And again, the error estimates are locally uniform. You're not allowed to let epsilon go to 0. Right? This is what this means. So, while such complete exponential sums have been studied quite a lot, though not by analysts, mainly by number theorists, right? So maybe not exactly those, because then it depends on what kind of polynomial you put here, right? What polynomial you look at. You can take any polynomials with integer coefficients, right, of the variable L and look at the same kind of sums and try to understand what they do. But of course, what you need to analyze now this is to understand. So these are numbers, right? These are once P and Q are fixed, these are just fixed numbers, okay? So when you analyze this, what you need to understand, one of the basic things is you need to understand whether this function really is inside the sum. So you need to understand whether this vanishes or not, right? Whether these exponential sums, of course you'd be happy to know their values, but do they vanish, right? There's no asymptotic behavior here anymore, right, in this limit. And so the first thing we're going to do is the simplest, actually it's not the simplest frequency, it's the frequency when omega is 0, okay? So assume that P equals 0, Q equals 1, so there is some condition. So of course, look at the form of epsilon. This means that you have a very special epsilon, right? Epsilon is 3 divided by pi squared divided by 3, right? Times an integer. Okay, so it gives you a very special epsilon. Well, let's first analyze this. And in this case, what one can show is that, well, you can actually, using the same techniques, actually not exactly by the theorem, but the same techniques, you can rewrite the inverse of the reflection coefficient up to some function depending only on epsilon, not on energy, so not changing the zeros. You can rewrite it in the following way. So you have the following asymptotics for this function, right? And this in particular means that, well, you get the following description for the resonances, right? If you look at real part between 0 and epsilon and imaginary part negative, and now you look at the resonances that are very negative, okay? So y is large. As everything is in E over epsilon, I wrote imaginary part of E less than minus epsilon times y. Okay, what you show is that the resonances that are below this line, inside, of course, for real part between 0 and epsilon, otherwise it's repeated periodically, they are actually located inside such an interval. The real part is located in such an interval. And you can compute an asymptotic of their number, right? Of the number of these resonances. The difficulty with epsilon, so you don't get something very precise. In the sense, you're going to see when omega is not 0, what we're going to get is actually an asymptotic formula for the resonances, right, under certain conditions. But in this case, the difficulty comes from the fact that this thing, right, if you look at it, it's actually depending on the first Fourier coefficients of 1 over r. It doesn't depend on the faraway series. It doesn't depend, if you want, on the oscillations e to the minus 2i pi omega m cubed, right, because omega is 0. Whereas if you look at the case omega non-vanishing, then what you can show is that, well, these sums, so something simple you can say, if you sum over all the m's, right, just write the formula here so you can do the summation. So this is e to I PL cubed minus ML divided by Q, and this is what I call QPM. So if I take, and this is sum over L, from 1 from 0 to Q minus 1. So of course, if you take the modular square of this, and sum it over M, well, you get that this results in Q squared. Right? You just have diagonal terms. No Q squared because I didn't normalize. I did not normalize by 1 over square root of Q. The usual thing is that you normalize this by the expected value, which is 1 over square root of Q.
You get 1.
No, here you get Q squared. Try it. You just do this, and what you get is diagonal terms, right? But you have Q of them, right? And you get Q squared. So if you take the 1 over square root out, then you get Q, as you say. I let you do it.
Oh, you sum the
Exactly.
sum, you sum the sum.
Exactly. I sum the
Then
sum.
You sum the sum, not just.
I sum the sum. I don't know any. I don't
Oh,
know.
sorry. You should normalize by 1 over
Exact-
q, not take the square root q out. You should normalize by 1.
If you want, you can.
Sorry,
You can.
it's
Sure.
correct, Sorry, I'm stupid.
Yeah.
Yeah.
Then you can.
Sorry.
But this is fine.
Yeah.
And so the one thing is that you can show using, well, actually a famous estimate from number theory that actually this implies that many of these things are not vanishing. Using just this bound, what you can show is that using Roy's estimate on cubic exponential sums, you can show that actually there are at least, when q is large, q to the 2/3, right, of these q sums that do not vanish, right, and this for any fixed p. And now this is a picture, right, these are 3 pictures actually, of what happens to these SPQ and SQ of P and M. And what did I draw? I drew the following thing. In the ordinate, it's the index M. In the abscissa is the index M. In the ordinate, it's the index P. And a dot is green every time the function does not vanish, SQPM does not vanish, and it's black if it vanishes. And here you have the picture of what happens for q equals 58, for q equals 59, and for q equals 60. Right? And well, what does 59 have special? It's a prime. Right? 59 is a prime, and you see that it does not vanish for any values. Okay? And that's a conjecture. Actually, we tried on the computer. We went up to primes. I think the largest I was able to take on my laptop was 603, and it worked. It never vanishes, right? For primes, it never vanishes for this special function. Okay? Tried to prove it, but with no success for the moment. And I really ran out of ideas. Actually, we looked into books, and tried to prove it by using the same method, but we're not able to do that. I asked some analytic number theorists, but nobody actually knew about the result. I could just show the numerical evidence. And, well, good question. So nevertheless, now we know that many of these are non-zero, and so let's assume that they are non-zero for at least 2 values of n, right, which is certainly the case in these pictures. And then we can show the following thing. Take m1 and m2 such that they are non-zero for m1 and m2, and they are 0 in between m1 and m2. Then you can show that for large imaginary part, you have resonances in the vertical strip, in this vertical strip. So the imaginary part is below minus y epsilon, y very large, and the real part is between m1 over q epsilon, m2 over q epsilon. And in this strip, the resonances have the following asymptotics. Right? So you can get asymptotics for the resonances, the very low line resonances, from this Fourier coefficient expansion of the reflection coefficient. Right? Of course, the representation right here is not uniform in P, Q, M1, and M2. It's only uniform if you require that both these 2 functions remain small, but of course this one, you're going to have a hard time controlling. Right? That's really the difficult part. Okay, I think this was all I wanted to say, and I thank you for your attention.
You had many questions. Was there any other questions, comments? Sure.
So can you explain again how the non-zeroness of these exponentials are? Because they appeared in the sum.
Exactly.
And you wanted that to vanish somehow.
Exactly.
Can you
So the idea is the following thing. Oops. Inside the sum, right? So you take 2 consecutive coefficients, right, that do not vanish.
Yeah.
So, and you essentially put your point psi, which is the real part, in such a way that these 2 will give you the main contribution to this. So it means that to look at the zeros of all this series, you just need to keep the 2 main terms, right? Because what makes them to be the main terms is the asymptotic imaginary part. The rho goes to infinity, right? And so this is, and so you see that you have 2 terms that come singled out, and all the other ones will be much smaller because of this term.
But then you want them to be.
And then you want to look at the zeros, but you have what you have. You have that actually, what this will show you is that this function inside this region, I won't describe again, is going to be close to the function, which is just the sum of SPQM1 and the term corresponding to M1 here, plus SPQM2 and the term M2 corresponding to that. And so you have two functions that are close to each other. One of them you know the zeros, while the other one, these are analytic. The other one you can use Rocher theorem, for example, to know the zeros. Right? And this is how you prove. So this is the magic of analytic functions. Right? So this is why you can analyze this. But we don't know, for example, how to analyze a thing especially when omega is irrational. What you can do is you can play with a computer again, and you can try to look at what's happening to these sums when omega is rational. And of course, you see that they depend very heavily on the number theoretical properties of omega, right? How these sums behave and what the zeros are. So this you can play with on the computer, but we're not able for the moment to extract any theorem about resonances from this. Yes, sure, please.
Yeah, something which I missed probably. You see, your sums which you end up with, they are nice cubic trigonometric sums,
Yes.
which are studied. The sums which you are started with, you got started with if you go back to the
Yes.
slide. Because these decaying parts, decaying factors,
Exactly.
minus m. So how
Well, there are
how
still.
you reconcile these things? Because if the coefficients decay very fast, it's completely different behavior. It's not.
Yeah, but the thing, you see, first, this does not decay this decays, right? But it does not decay very fast in the sense that log m only decays slowly.
You have m log.
Exactly, but you have another m which is coming here. The point is that what you are playing is, you are looking at the imaginary part very negative.
But m log m beats up m.
Of course, at infinity, but locally it doesn't. When m is going to be of a size of, what you're doing actually to get from here to there, right? What you're doing to get from here to there is actually, technically, you rewrite the thing, right, and try to compute it, using, you rewrite the sum here and try to compute it using Poisson's formula, okay? And in Poisson's formula, you get integrals coming out, right? And these integrals you analyze using the, what is it called? Now I can't remember the name.
Stationary effect?
Not stationary. No, it's not stationary. It's in the complex. It's the mountain part. Not the mountain part. Steepest descent. Exactly. You use the steepest descent in the complex to analyze this, right? Asymptotically, when the imaginary part of E goes to minus infinity, right? And it's by doing this transformation that you actually end up with the other function, right? So within the Poisson formula, there's some magic, quote unquote, going on.
No, but I mean, so first of all, when omega is rational,
Yes.
then you have periodicity in the summation. So your cutoff becomes less relevant because you are summing over quite a big window when E is large.
Sure.
So the fact that you truncate with a square or if you truncate with a sort of smoother cutoff, that doesn't matter so much because you use the periodicity of the function in the exponents. And then if you have an irrational omega, what you were talking about, it's a similar argument that the cutoff smoothing doesn't affect so much the size of the exponential sum. It does, of course. I mean,
Of course it does.
But
Sure.
it's morally, it's sort of. But for the rational case, it's sort of, I guess.
Yeah, you're right.
clearer.
Any other questions? Does it make sense to ask questions about non-smooth potentials?
Of course it makes sense.
Like
And it makes
delta
very much
function.
sense, actually. And so let me come back to the first story, actually, that I have here on the board. It makes very much sense. I mean, as I said, we have here some very smooth potentials. And one of the things that are well known for these very smooth potentials is that if you have infinitely many gaps and look at the gap length, right, which are actually blended in this picture, you see that actually these tori here have roughly their radius, right, is, well, more or less given by the gap length. I don't say it's equal to, right, but it's more or less given by the gap length. But it's well known that if the potentials are very regular, the gap length decays very fast, right? For example, for analytic potentials, it's known that it goes to zero exponentially fast, right? If you have some CK potentials, right, you get that it goes to 0 and to minus K. But of course, the width at the speed at which this goes to 0, right, determines, as we say, if you really believe, I mean, this picture was only proved for a finite number of gaps. But if you take infinitely many and you believe that this picture is still correct, what should be the width of the first resonance? It should be something which is roughly of size the sum of the length of the gaps. Right? If you take analytic coefficients, nice, gaps are summable, the length of the gaps is summable, you get something with finite distance. But if you decrease the regularity of your potential, well, the gaps will become less and less summable, right? And as far as I remember, I think the limit, I mean, the threshold point is h minus 1. If you take a potential, which is in h minus 1, sublevels space order minus 1, or let's say if you take h minus alpha, alpha larger than minus 1, you get something which is summable. And if you take below, it's not summable anymore. But if it's not summable, it means that this coefficient c actually should be actually plus infinity. So it means that your resonances will sit on the spectrum. The imaginary part should be 0. And there is a famous conjecture saying that if you take such an operator, right, with a potential which is h minus 1, I think it's h minus 1, I don't remember exactly the exponent, but it's h minus 1, then the spectrum should cease to be purely absolutely continuous. Is it purely? I mean, it's known that if the potential is, if you take sum of delta primes periodic, then it's not absolutely continuous anymore. But there's a region in between, so this is delta primes, I think it's h minus 2.
Frédéric,
Yes.
what about the direct comp?
Direct comp is fine actually. This is h minus 1/2, right? I think direct comp is h minus 1/2. So this is fine. It's known to be AC, but the limit is a little bit lower. It's delta prime. No, not delta prime. It's in between. It's between delta and delta prime. Okay, somewhere in between. And there, what you'd expect is that actually the resonances come up to the real axis, and well, they can be so nasty just as for Dirac, the Dirac prime derivative of Dirac com, where you know that the spectrum is pure point. Actually, it's not going to be AC anymore. And there are some threshold in between, but I don't think, I mean, this is also, it's also linked to conjectures, it's also linked to the analysis, asymptotic analysis that has been done for this. Of course, no conclusive result, as far as I know, no conclusive results were obtained. Well, in this analysis, what you also see coming out is cubic exponentials, not as sum, but more as cocycles. Right, to say you have cocycles, where the cocycles are of cubic exponentials, so there are some kind of non-linear analog, what do I want to say? Truly two-dimensional analogs of cubic sums, right? Not non-linear, but truly two-dimensional, right? Because it's really a product of matrices.
Non-abelian, right?
Exactly, non-abelian. Thanks very much. That's what we're looking for. It's non-abelian analog, right, of these exponential sums. But as far as I know, this was never rigorously analyzed. I mean, there is a paper of Life which has heuristics in it, but there is no control of what's happening to the remainder terms, as far as I know. Sure.
So, final gap conditioning can happen for quasi-periodic Are there experiments or intuition about the quasi-periodic finite gap situation?
It's finite band.
Well, it's the same thing. It's the same thing. Finite gap, finite band is the same thing. In the case of quasi-periodic, actually, I don't know. That's a good question. Sure. The analytic. Yeah, no, I know that. That's interesting. No, I didn't think about that, but I don't know. Actually, I don't know because I mean, for example, the semi-classics, right, uses Bloch theory, right? They use Bloch-Floquet theory to get the semi-classics. So in the quasi-periodic case, this is not going to survive, and I don't know what to replace it with. Right, so I'm not sure whether you should expect actually this kind of semi-classics to stay true.
I mean, you mentioned some experiment. That's why.
Oh, you mean experiments? This I don't know at all actually. So for experiments, no, this I don't know. But moreover, an experiment, I mean, I think when you generate a potential, it's going to be pretty hard to verify whether it's a finite gap or not, right? You're pretty likely to get a potential which is infinite gap. Right. So sure.
So if you insert a periodicity into this derivative term, will everything fall apart?
Periodicity in the derivative term?
No problem, not d2x, but ddx, a ddx, right? A is a periodic function.
Oh, you put the periodic function here and you remove the potential? So you take a second order perturbation of the Laplacian? Well, then I don't know. Yeah, this is going to be a, well, I don't know. Really, I don't know. I think it's going to fall apart because this picture, if you believe in this picture, the picture here is going to be completely different, right? And that's really the one thing that things are relying on. Moreover, yeah, no, this is, I think it's going to be quite different, yeah, definitely.
Was there any other questions? If not, let us think.
Well,
Unfortunately, I'm next to Wisconsin.
yeah, unfortunately, Stas Molchanov is sick, so we're going to reschedule his talk in a couple of 2 weeks from now. Not next week because it's already full, but